Okay, I want to take a minute to talk about eigenvectors of the differential operator. So a while back we talked about this a little bit. The set of all continuous differentiable functions forms a vector space. And let's call that C, C for continuous. One thing, C has infinite dimension, and its vectors are functions. So like all the polynomials of all degrees would be included in there. So like P, the set of all polynomials, would be a subspace of this thing. But this contains not only polynomials, but it includes all the other continuous functions like sine, cosine, e to the x, all that kind of stuff. The differential operator is a linear transformation. And if you go back to the definition of what makes a linear transformation, you know, if you take the derivative of f plus g, you can split that up into the derivative of f plus the derivative of g. And also if you take the derivative of a constant times a function, you can pull that constant out front. So anyway, the differential operator is a linear transformation. But d dx can't be represented as a matrix on C because it would be infinitely large. So this is what I really wanted to get to here. What are the eigenvectors and eigenvalues of this thing? Now, in this case, our vectors are functions. So instead of calling them eigenvectors, sometimes we might call them eigenfunctions in here. So the question here is, what are the eigenvectors? Well, in order to do that, you'd have to find some function f of x that satisfies f prime of x is equal to some constant times f of x. Can you think of any function that works like that? Well, if you take this c and get rid of it and set it equal to 1, can you think of a function that's f prime of x equals f of x? There is one function that does that, other than the 0 function. That's f of x equals e to the x. This is an eigenfunction of the differential operator. And what's the eigenvalue that goes with it? Well, in this case, it's 1. All right. Well, can you think of a function that f prime of x is equal to twice the original function? If you think about this a little bit, I think f of x equals e to the 2x will come to mind. Because if you take f prime, you get e to the 2x times 2 by the chain rule. So you get 2 times f of x. And maybe instead of writing f prime for my notation here, maybe to be a little more consistent with what we've been doing, we could say the derivative of like that. So e to the 2x, this is an eigenfunction with eigenvalue 2. And I think this gives a little bit of idea of why eigenvalues and eigenvectors are important. You know, e to the x, or e to a constant times x, that's one of the easiest things there is to take the derivative of. And the reason that it's easy is because it's an eigenfunction. Maybe I shouldn't say it's the reason it's easy, but those two things are definitely related. With matrix multiplication, the eigenvectors are the easiest things to multiply by. So anyway, if you're a math major, or if you take any sort of higher analysis, that kind of thing, this kind of concept is going to come in again, and it'll probably come in if you go into engineering as well. So anyway, I just wanted to mention that, and I think I'll stop this section here.